Dear students, welcome. Today we are going on a deep dive into four absolutely critical pillars of the computational fluid dynamics, the types of the grids, solution consistency, error analysis, and numerical stability. So by the end of this particular session, you will not only know the definitions but also understand how these concepts interact through the Lex equivalence theorem and how to apply this particular knowledge to diagnose and improve your own simulations. So let me give you a roadmap. We will start with the grids, the skeleton of any CFD simulation. We will compare the structured, unstructured, hybrid, overset, and the adaptive meshes, discussing their strengths, weaknesses, and when to use each. Then we move to consistency, the mathematical guarantee that our discrete equations actually represent the physics we want. Next, we will dissect the errors, modeling, discretization, iterative and round off, and learn how to estimate and control them using the techniques like Richardson extrapolation and residual monitoring. Finally, we will tackle the stability, covering the CFL condition, explicit versus implicit schemes, and von Neumann analysis. We will close by uniting everything with the Lex equivalence theorem. So let us start. In CFD, the grid is where the physics meets computer. The governing equations like Navier-Stokes equation, the Euler equation, etc., are continuous partial differential equations. To solve them numerically, we must discretize the domain into a finite number of points or the cells. The discrete grid actually dictates the resolution of flow features, the accuracy of the gradient calculations, the stability limits, and the computational cost. A poor grade can make even the best solver fail. A good grade can make a modest solver shine. So let us begin with the structured grades first. The defining characteristic is that the grid points can be indexed with the integer triplets like ijk, and each interior point has exactly the same number of neighbors in each direction. This regular connectivity is implicit. We You don't need actually to store the connectivity table. Now, as far as the shapes are concerned, in 2D we say the quadrilaterals, in 3D we say the hexahedra or the bricks. So the simplest case is a Cartesian grid where all lines are parallel to coordinate axis. For curved boundaries, we use curvilinear or the body-fitted grids. Coordinate transformation maps a rectangular computation space to a curved physical space. The grid lines becomes curved but remain topologically rectangular. uh, we have three major advantages. First is that it is memory efficient. Only coordinates need to be stored but not connectivity. uh, the second is that the fast solvers, line implicit methods, ADI or the alternating direction implicit, and fast Poisson solvers work beautifully on it. Low numerical diffusion when aligned to the flow. What are the disadvantages to it? We have two major disadvantages. Extremely difficult to generate for the complex geometries, for example, a human face or a engine block. Local refinement is very messy. Refining one area forces wave-like perturbations across the grid. So as an example, if we look, a structured grid around an airfoil requires an O grid or C grid topology. The grid lines wrap around the leading edge. Generating this manually is an art. So, and now let us discuss the unstructured grids. Here the connectivity is arbitrary. Each cell can have a different number of neighbors. We must store a list of which nodes belong to which cell and which cells neighbor each other. As far as the shapes are concerned, we say the triangles in 2D, tetrahedra in 3D. So sometimes pyramids or prisms are used in transitional elements. Tetrahedra can also fill any volume automatically. So we would be discussing the advantages first of the unstructured grids. It We have the unmeshed geometric flexibility, the automatic mesh generations, Delaunay advancing front can mesh almost any CAD geometry. Easy local refinement, just split the cells in the region, and it naturally supports the solution adaptive refinement AMR. Now, the disadvantages to it that higher memory usage would be there, connectivity tables would be forming, the slower solvers due to the indirect memory access and less efficient linear algebra. And the third and the last disadvantage to it is the potential for higher numerical diffusion because cell faces are not aligned with the flow. So here is a practical tip. Unstructured grids are the default for industrial, automotive, or and aerospace applications with complex geometries, but always check the mesh quality matrix, skewness, aspect ratio, and the orthogonal quality. Now moving on to the hybrid type of the grids, these type of the grids combine the structured and the unstructured regions to get the best of the both worlds. A classic example include the near walls where boundary layers have very strong gradients. We will use the prism layers, structured layers of high aspect ratio, hexahedra or the prism grown from the wall surface. The rest of the domain is filled with the tetrahedra. So why this works? The structured prism layers resolve the rapid velocity and the temperature variation normal to the wall efficiently and very accurately. The unstructured core handles the complex geometry far from the wall. Other hybrid configuration include the structured block around the wing, unstructured around the fuselage, the structured duct, unstructured valve region. While the on overall, if we discuss the hybrid grids, are the workhorse of the modern industrial CFD. Almost every commercial solver offers the prism layer generation. So moving on to the overset or the chimera grids or chimera grids. So overset grids consists of multiple independent grids that overlap each other. This is a background grid covering the whole domain, and one or more component grids that move relative to it. For example, a rotor blade grid rotating inside a stationary background grid. So how it works: at each time step, the solver identifies the whole cells where one grid is obscured by another, and interpolation points where data is transferred between the grids. So this solution is computed on each grid separately, then coupled via interpolation. So advantages to it are that we have no mesh deformation or regeneration for the moving parts. For each component can be optimally structured. For example, high quality O grade around the blade structure, great for the multi-body problems like the store separation, helicopters to rotors, or the piston engines. Challenges for the this type of the O grade or the overset grades include the interpolation that introduces the additional errors. Careful setup is needed to ensure the conservation and avoid the orphan cells, more often complex to implement. So finally, we move on to the adaptive mesh refinement, which is AMR, a grid that changes during the simulation based on the solution itself. The solver continuously estimates a local error indicator, for example, gradient of the velocity, curvature of the shock wave, and refines the cells where error is very much high and coarses where the error is low. So types of this particular AMR or the adaptive mesh refinement is the H refinement. First of all, it splits a cells uh, into smaller cells. The second, P refinement increase the polynomial order within a cell, often called as HP adaptivity. R refinement refers to that it moves the nodes without changing topology. It is less common. So AMR in action is actually simulating a shock tube. Initially a coarse grid, when the shock forms, the solver detects the pressure jumps and refines cells in the shock region. As the shock moves, the refinement follows it. So advantages is that it is extremely efficient. You get high resolution exactly when where needed. One disadvantage to this particular type of the technique is that complex data structures, load balancing for parallel computing, and potential for introducing errors during refinement and or coarsening. So key insight is that AMR is not a beginner's tool, but for problems with localized features like detonation, multi-phase interfaces, atmospheric plumes, it is transformative. Now, moving on to the second part, which is the solution consistency. Consistency actually answers a fundamental question as we refine the grade delta x and delta t actually when approaches to zero. Does the discrete equation we solve on the computer actually approach the original partial differential equation? So if the answer to this particular question is yes, the scheme is consistent. If no, you are solving the wrong equations no matter how fine your grade is. So to check the consistency, we use a Taylor series expansion, and considering the forward difference for the first derivative, we can expand and subtract and ultimately divide it by delta of x. So the term beyond du by d of x over here form the truncation error. The leading term is delta x by 2 d square u over d of x square, because it contains delta of x as to the first power. So we say that this particular scheme is first order accurate. The error is proportional to delta of x, so we write the truncation error equals to O bracket delta of x, because it's of the first order. So as delta of x approaches to 0, this truncation error goes to 0. Hence the forward difference is consistent. A scheme is consistent if its truncation error tends to 0 with grid spacing. Now, moving on to the order of accuracy, higher order schemes have truncation errors like of the order of a second order, or O bracket delta of x cube, which actually represents a third order scheme. So, for example, the central difference as represented over here. So, this is a second order accurate. On a given grade, a second order scheme will converge faster than a first order scheme as you refine the mesh. However, a higher order does not automatically mean better. It can be less robust for shocks or poorly resolved gradients. So, in practice, how do you verify the consistency? We would have the first of all the theoretical analysis over here. So, in theoretical analysis, we derive the truncation error using the Taylor series. Secondly, the manufactured solution, we would choose an arbitrary smooth function that does not necessarily satisfy the original PDE. So we plug it in into the discrete scheme and see if the residual goes to 0 at the expected rate as you refine the grid. And the third step you would be necessarily do to verify the consistency is the grid refinement studies. We would solve a problem with the known smooth solution on a sequence of grids, compute the error term. If the error decreases as delta x superscript p, where p matches the formal order, consistency is confirmed. So when we have a warning situation, uh, is when a scheme can be consistent but not stable. That leads to a non-convergence, which we will cover in the last part of this particular lecture. Now we move on to the reality of the CFD, which is the error part. No simulation is exact in actual. Our job is to understand, quantify, and reduce the various error sources. So, modeling error is the difference between the actual physics and our mathematical model. Did we use the incompressible Navier-Stokes when compressibility effects are non-negligible? For example, when Mach number is greater than zero point 0.3. Did we choose a turbulence model that is inappropriate? For example, using the standard K epsilon model for a flow with strong separation or large streamline curvature will introduce significant modeling error. And the third question, which we would be asking for the modeling error, is that did we ignore the radiation heat transfer when it matters the most? So the key point over here is that the modeling error cannot be reduced by refining the grid. So it can only be addressed by improving the physical model. Validation against experimental data is the only way to quantify the modeling error. The second type of the error is the discretization error, which is the difference between the exact solution of the PDE and the finite exact solution of the discrete algebraic equations. So its main component is the truncation error, but it also includes the errors from boundary condition discretization and grid non-uniformities. Estimating the discretization error is actually a part of the Richardson extrapolation. Suppose we have a solution f of h on a grid with characteristic size h, Assume the exact solution as displayed over here by this particular equation where P is the order of accuracy. Compute a second solution on a refined grade FH by 2. Then this gives an estimate of the exact solution. The Grade Convergence Index GCI is a standardized error band which we can represent by this particular equation. GCI equals to f of s fh by 2 minus f of h divided by 2p minus 1 multiplied by 1 over f exacts, where f of s is actually a factor of safety factor, typically 1.25 or 3. The GCI actually tells you a percentage how far you likely are from the grid independent solution. So here is a practical advice that always perform a grade convergence study for at least three grades: coarse, medium, fine. If the grade convergence index is too large, refine the mesh. uh, Now we move on to the iterative type of the error. Most CFD solvers solve the non-linear algebraic equations iteratively, starting from an initial guess. They update until the changes are very small. Iterative error is actually the difference between the current iterate and the exact solution of the discrete equations. Uh, then we see the residuals, the most common metric for a conservative equation. The residual is the imbalance left after plugging the correct current solution into the discrete equations. Identify ideally the residuals drop by several orders of magnitude, typically 10 raised to power minus 6 for steady problems and 10 raised to power minus 3 to 10 raised to minus 4 for the unsteady type of the problems. But residuals alone can lie. They may plateau due to round off or poor conditioning. Always monitor an integrated quantity like lift, drag, pressure drop, etc. So if that quantity stops changing while residuals are still high, you might be fine. Conversely, low residuals but drifting forces indicate a problem. Convergence tolerance, we don't set the residual targets lower than the discretization error. You are then just iterating on noise actually. Then another type of the error is the round of error. Computers actually represent the numbers with finite precision. Typically 64-bit double precision gives about 15 to 16 decimal digits. Each arithmetic operation rounds the result. A round of error accumulates. And then we have a simple question over here that when does the round of error round off matter? In very large simulations with millions of operations, especially if the solution involves subtraction of nearly equal numbers, which is the catastrophic cancellation. So the second scenario is that when you try to drive the residuals to extremely low levels, for example 10 to the power minus 14, uh, for such an order of the residual, the discretization error is often 10 to the minus 3 to 10 to the power minus 5. So changing this particular round off is pointless. In ill-conditioned systems, for example, high aspect ratio cells, the mitigation of this particular round of error, we use the double precision. Single precision is very rarely enough for the CFD. On the other hand, so to avoid excessively tight iterative tolerances, use good preconditioners for the linear type of the solvers. Then we have a process which is called as a verification and validation process, V&V. These two processes are the gold standard for credible CFD. Verification means that are we solving the equations right, while the validation means that are we solving the right equation. So there is a difference between the two processes. In verification, the code verification, we find the bugs by the method of manufactured solution, and we actually verify the solution too. Quantify the numerical errors, which is the discretization iterative round of the grid convergence study, and the GCI are the verification tools. While in validation, when we ask that are we solving the right equation, so we compare actually the simulation results to reliable experimental data, typically done for a specific class of flows, for example the turbulent flow over a backward facing step. And it also quantifies the modeling error. So important point over here is that the verification must come before validation. A non-verified code or an insufficiently resolved grade makes validation meaningless. Now, moving on to our numerical stability part of this particular lecture, now we enter into a realm of stability, perhaps the most frustrating issue of the for the CFD practitioners. You set up a perfectly consistent scheme, but when you hit run, the solution explodes to infinity. This is the instability. So a numerical scheme is stable if the small errors such as the round off, truncation, or the perturbations in it do not grow unbounded as the solution advances. So in stable schemes, errors decay or at least remains bounded. In unstable schemes, on the other hand, the errors are amplified exponentially. So stability is a property of a numerical method combined with the problem boundary conditions grade time step. So a scheme that is stable for one problem may be unstable for the another. Now, the CFL condition is the most famous stability condition, which is often abbreviated as Courant Fredericks Levy condition, CFL condition, named after the three mathematicians who discovered it in 1928. For the 1D linear convection equation u of t plus c u of x equals to 0, this condition is that it must be equal to c delta t divided by delta of x, and this particular ratio must be less than equal to 1. What it means physically is that in one time step, a fluid particle should not travel farther than the distance between the two grid cells. If it does, the numerical scheme cannot obtain the necessary information from the neighboring cells, leading to instability. So for multi-dimensions, this CFL condition generalizes to another type of the equation for the delta T, which is hereby represented. And we can see over here that for diffusion heat equation, the condition is lambda delta T over delta of x whole square must be less than equal to half, which is even more stricter than this. Now, moving on to the explicit versus implicit schemes and discussing its stability. Explicit schemes, the value at the new time step depends only on known values from the previous time step. They are simple to implement but have strictly stability limits. Typically, the CFL condition forces tiny time steps, making them very inefficient for the steady or the slow flows. While on the other hand, implicit schemes, we have the new time step values are coupled in a system of equations. They require solving a matrix at each time step, but they can be unconditionally stable. Stable for any time step size, even huge ones. For example, the backward Euler method for the heat equation is unconditionally stable. Now, here is a trade-off that explicit equals to the cheap per step, but many steps involved in it. While on the other hand, implicit would mean that it would be expensive per step, but can take giant steps. So for unsteady flows with fine grades, implicit often wins. For highly transient flows with sharp features, for example, a blast wave, explicit may be preferred because it better captures the physics. Von Neumann stability analysis or the Fourier stability analysis is the standard tool for these linear constant coefficient problems. Steps involves are the four steps. We in the first step assume the error can be represented as the sum of the Fourier modes, that can be represented as e raised to the power I kx. Substitute one mode into a discretized error equation, derive the amplification factor and how much the mode grows per time step. And lastly, we for stability, we require the determinant of this particular amplification factor must be less than equal to 1 for all wave numbers k. For example, for the forward time, central space FTCS scheme for the heat equation, von Neumann stability analysis yields G equals to 1 minus 2D 1 minus cos of k delta of x, where D equals to alpha delta t divided by delta of x square. So this condition, which means modulus of the amplification factor must be less than equal to 1 for all k, leads to the D less than equal to half. So the diffusion stability limit. Now, what are the limitations? Limitation is that von Neumann stability analysis only applies to the linear problems with periodic boundary condition and constant coefficients. For non-linear problems, we linearize locally and we use it as a guideline. So, now, up till now, we have covered the grids, consistency, error, and stability. Now we tie them together with the most important theorem in the numerical analysis of partial differential equations, which is the Lex equivalence theorem. Statement for the linear initial value problems is that a consistent finite difference scheme for a well-posed linear partial differential equation is convergent if and only if it is stable. In other words, consistency plus stability is equal to convergence. So let us unpack the terms. Convergence, as we refine the grid delta of x delta of t approaches 0, the numerical solution approaches the exact solution of the PDE. So this is our ultimate goal. What is consistency? The discrete equations approximate the correct partial differential equation, which means that the truncation error approaches 0. And then lastly, stability means that the small errors are not amplified unboundedly. So the theorem tells us that if we have a consistent scheme, the only thing standing between us and the convergence is stability. Conversely, if a scheme is unstable, it cannot converge regardless of consistency. Now, here are the practical implications. When we develop a new scheme, first check consistency via the Taylor series, then analyze the stability via von Neumann or the energy methods. Once both are satisfied, convergence is guaranteed. In practice, if your simulations do not converge as you refine the grid, you either have an inconsistency, for example, incorrect boundary condition implementation, or instability, for example, the CFL violation. And thirdly, the theorem extends to many nonlinear problems throughout formally proven, though not formally proven, but the insight remains: control your truncation error and keep your scheme stable. Now, here are the final concluding remarks that always perform a great refinement study. It is your best defense against the discretization error. Monitor the residuals and the integrated forces. Do not rely on the residuals alone and respect the CFL condition for the explicit schemes. For implicit, still use a reasonable CFL to maintain the temporal accuracies. And when we validate against the experiments, modeling error is often larger than the numerical error. So thank you very much for your attention. See you next time in next lecture. Take care.